All right, welcome back everyone to our next Geophysics and Tectonics seminar. I'm excited to announce that our speaker this week is Iris van Zelst, who's currently a postdoc at the University of Leeds, and she'll be talking to us about modeling tsunamigenic earthquakes. So I'm excited for this. Whenever you're ready, Dr. van Zelst, please go ahead.
Thank you very much. Yeah, I will be talking about modeling tsunamigenic earthquakes. This is mostly my PhD work, and I just want to stress that, first of all, I'm really happy that I can give this talk, so thank you for having me. And it really has been a collaboration within a team. So these are all the important names, and just to really hammer down who they are, these are the people that have been mostly involved in this work. There have been some other people too, but I'm not specifically highlighting their work as much during this talk. And yeah, we have Stephanie, Leo, Betsy, Aniko, Thomas, Stefan, Ilona, and Alice. And yeah, whenever they have a significant contribution or they've been the lead on the projects that I will be sharing, because they've been doing very cool things. So I wanted to share some applications. You will see their pictures popping up and their names. Yeah. So let's start at the beginning. Tsunamigenic earthquakes. What are they? They're earthquakes that cause tsunamis, simple as that. And typically, the ones that we consider in this talk, they occur in subduction zones on thrust faults. So I hope the video works over internet, but we'll see. Here we have an oceanic plate that goes towards an overriding plate, and over hundreds of years, there is a locked portion of the fault where stresses build up until at some point the stresses reach a strength of the rock. Then there is an earthquake that facilitates movement that goes with some surface displacements, and because there is an ocean or a sea on top, you get a wave in the ocean that travels towards the beach, and then you get a tsunami with inundation and flooding. So, pretty simple. Typically, as what you've seen in the figure just before, you think of an earthquake as a point source. So, like in this very small GIF, you have a drop that drops into the water, and you get a very easy circular pattern of waves. And that is usually how earthquakes are shown in the media and stuff. But actually, it's much more complicated than that. And an earthquake propagates along a fault. So it's more like a boat that travels in the ocean or in the water, where you have a very complicated pattern of waves in its wake. So that is important to remind yourself of. And then just to kind of show you what tsunamigenic earthquakes are and how they behave, this is a little video of the wave propagation of the slip rate here that Alice made of the 2004 Sumatra Andaman earthquake. And having said this, I just want to mention that what I've just mentioned to you, we understand the broad strokes of the tsunamigenic earthquake process, right? We know you need stress, you need to know the strength of the rock, there's nucleation, things move, you get waves in the ocean. Okay, but these are just the very broad strokes, because there's a lot of things that we don't understand as well. For example, in 2004, during this very same Sumatra earthquake, it lasted exceptionally long, like many minutes long. And we didn't know that earthquakes could continue to shake so intensely for so long. So that was a surprise. Another famous surprise was the 2011 Tohoku earthquake, where the tsunami that was generated was much larger than we had expected, which, had a lot of complications later on when the seawalls built for the Fukushima nuclear power plant did anticipate for tsunamis, but not such high tsunamis. So the facilities flooded, and in the end, there was this major nuclear disaster. Then, just looking at some statistics, 75% of the tsunami warnings in the last 55 years were false. So although we know something and there is a tsunami early warning system, clearly it doesn't always work. And you don't want to warn people too often, because at some point they will just not listen anymore. And at the same time, tsunami alarms have also missed some dangerous tsunamis. So it's not that we're warning every time and people can evacuate and it's always fine. So, many things we don't know. Now, it's difficult to obtain data, so And with my expertise, what I like to do is do modeling. And modeling basically means that we use computational methods to solve equations that describe the physics of a process. And the processes involved in tsunamigenic earthquakes, as I've just shown, occur all on very different time scales. So that means in the numerics, the computer doesn't really like big contrasts. So typically many different modeling communities have been established around different aspects of the tsunamigenic earthquake. So there are lots of people doing subduction evolution modeling, lots of people that do seismic cycle modeling. Dynamic earthquake rupture modeling is a whole field, as is tsunami propagation and inundation modeling. Obviously, these distinct processes are connected. So there have also been some attempts to connect some of these processes by having one process that informs the other within one code or as a continuous feedback loop, or you can have two different codes that you couple to each other one way or in a continuous feedback loop. And these types of coupling have been applied to subduction evolution and seismic cycles together, seismic cycles and dynamic earthquake rupture together, and dynamic earthquake rupture and tsunami propagation together. But of course, ideally, we would like to do all four. And that is what my PhD was all about, combining all these four timescales to study the whole process of tsunamigenic earthquakes. And that is what we are going to be looking at today. So let's start with geodynamics, seismic cycles, and dynamic ruptures. We're going to consider two different codes. And very simply speaking, we have a geodynamic seismic cycle model, which we will abbreviate by SC in these slides. And we have a dynamic rupture model, which we abbreviate by DR. And we're going to use the output of the SC model as input for the dynamic rupture model. That's it. And some brief equations. The geodynamic seismic cycle model considers the conservation of mass and the conservation of momentum, as does the dynamic rupture model. And additionally, the geodynamic model considers the conservation of energy because it needs to account for the subduction evolution. There is a viscoelastoplastic rheology in the geodynamic model, whereas the dynamic rupture model is purely elastic in the case that I will mainly be showing you. And then, of course, the geodynamic seismic cycle model is very good at modeling tectonic stress buildup, which takes place over millions of years, and the seismic cycle on hundreds of years. And the dynamic rupture model is good at modeling dynamic ruptures, which take place on timescales of minutes and seconds and smaller than that. So I'm going to take you through how we couple these two codes. And we're going to start with how we set up the geodynamic model. This is the initial model setup. We have an oceanic plate, which gets pushed with 7.5 centimeters per year towards the continental plate. And there is a little accretionary wedge in between. And as input, we define this initial geometry, the velocity, the temperature profile, or the slab age, and the viscoelastoplastic rock properties that we get from the literature based on lab experiments. Now, what we do is we run this for about 4 million years with a time step of 1,000 years, which allows us to establish a steady state geometry of the subducting slab. And once the geometry is steady state, we gradually reduce the time step from 1,000 years to 5 years. And at that point, we have a seismic cycle in effect, and we get these episodic slip events. We don't call them earthquakes because it's a 5-year time step, which means that one of our slip events lasts for about 200 years, which is a long earthquake. But these slip events are what we imagine earthquakes are. And by coupling it later to a dynamic rupture model, we can actually resolve them, which is what we want. So how do we couple that? We have chosen one of the events to couple to a dynamic rupture model. And first of all, we need to couple the time step. So for which time step are we going to export everything to the dynamic rupture model? And we choose the time step for which we have spontaneous nucleation for the first time in the dynamic rupture model. Then the rock properties, the geometry and everything. This is what the geometry looks like. So it is the steady state subduction geometry that we've seen, but it says t equals 0 here because it's at the start of the event, and that's what we're going to consider from now on. So this is what it looks like. We have sediments here and a subducting slab here. Then the stress field, because as I mentioned, in order to get nucleation, the stresses need to reach the strength of the rock. So we need to know the initial stresses. And this is what they look like. And we can also have a look at them here. Here we have distance along the fault, with the 0 being the shallowest part of the fault. And here we have the stress and strength for the different models and the strength excess. And what I want you to take away from this figure is that here in the region of nucleation, the stress and strength are equal. So they have been reached, which means there is 0 strength excess. So that is where in the geodynamic model you get nucleation. And because we import this into the dynamic rupture model, we also get this nucleation there because these stresses and strengths are the same. In order to then export the strength to the dynamic rupture model, we not only need the cohesion that is included in the rock properties, but also the friction parameters. A bit tricky there because there is slightly different friction formulations in the geodynamic model than in the dynamic rupture model. So in the dots here show what actually happens in the geodynamic model during one event, and then there is healing. But we have a linear slip weakening approximation in the dynamic rupture model, and we make sure that the area below the curves are the same. And we have the same drop in friction. And then lastly, we need the fault geometry because the earthquake needs to propagate along this fault, right? It was this boat in the ocean. Again, a bit tricky because in geodynamic model, we're working with continuum mechanics, which means there is a continuum. So you, by definition, do not have any discontinuities like a fault. Bit of a problem, but what we do have is strain localization and so-called shear bands. So that's what you see here in the strain rate is where we have localized strain. And what we do is throughout the whole event, we pick where we have the highest strain localization. And based on that, we then plot our fault through that and smooth it a little bit so that it doesn't look weird due to the resolution. And then we get this megathrust geometry. And that is what we use in the dynamic rupture model. Okay, so now we have all the ingredients for the dynamic rupture model setup from our geodynamic model. So you have the rock properties, the stress field, friction parameters, and fault geometry. This is what it looks like. This is a zoom of the model where we're most interested in. And this is the P-wave velocity that I show you here. And in red, we have the megathrust that we're interested in. Okay, so then we can run this model, we get our earthquake, and we can have a look at how well we did this. So let's first try and see how well the two events compare, the many years long event in geodynamic model and the actual earthquake in the dynamic rupture model. So here again, we have our fault, our megathrust, and we're going to rotate it a bit and just make it flat. That is how we're going to plot it. So here we have distance along fault, with 0 being the most shallow part of the fault. And then I plot what happens on there with time, that's on the y-axis. And what I plot in this space is in this case the slip rate. Okay. And then in order to make it a bit more intuitive where we have different regimes, you can have velocity strengthening, velocity weakening. Here are some isotherms that define that. So here in this middle part, you have velocity weakening, which kind of promotes slip, while at the shallow part of the fault, you have velocity strengthening, which inhibits it. That is what it looks like for the geodynamic model. This is what it looks like for the dynamic rupture model. First thing to notice, different scales. So here we have an earthquake that lasts for hundreds of years. And here we have seconds, which is much more reasonable. Same goes for the slip rates, very, very low values, while here they're actually realistic. So that's great. And another thing we can immediately notice is that they actually nucleate in the same place, which makes sense because that is how we defined our input parameters, because we took those from the geodynamic model. But it is quite nice for the dynamic rupture community because oftentimes they struggle to define their initial conditions of stress and strength self-consistently. And here they just roll out of millions of years of convergence of subduction. And then it still works and we get this spontaneous nucleation. Similarly, what we see is that deeper into the fault, where we go from brittle to ductile deformation, which depends on the temperature in the slab here, we see that the fault stops slipping there. So there's no slip here anymore, and we see the same in the dynamic rupture model. And again, we have this spontaneous rupture arrest purely because of the mechanisms that took place in the geodynamic model, which again is great because typically dynamic rupture community struggles with doing that in a self-consistent way. So that is excellent. Spontaneous nucleation and arrest. Now let's have a bit of a closer look at the dynamic rupture model, because lots of things are happening there. There's lots of details here. For example, you see that slip rate increases sometimes, and this is all due to the seismic waves that, because we have this better time scale, we can actually look at the seismic waves. And in order to actually see them, we can have a look at some snapshots. So here we have the model at 10 seconds, and I'm plotting the horizontal velocity here. And again, here at the top, we have our free surface, and then we have our megathrust fault. And at 10 seconds, it looks like quite an easy earthquake. Clearly, the subducting slab is going towards the right, and the overriding plate is going towards the left, and it looks kind of simple. A bit later, 25 seconds, already a lot more is happening. We've seen that the waves that were going out from the fault here have since reached the surface, realize they can't go through the surface, and hence they are being reflected back towards the fault. So those are the wave fronts that you see here that are going back towards the megathrust. And if we look a little bit later still, we can see that most of the seismic energy is actually trapped in this accretionary wedge. So lots of things happening. And actually, this matters quite a lot. So we see that these seismic waves get trapped in the accretionary wedge, and that influences the amount of slip and the slip distribution. So in the geodynamic model, we have about 8 meters of slip, and most of the slip is located in the nucleation region. In the dynamic rupture model, however, we have much more slip, about 58 meters, and most of the slip is located in the shallow part of the fault. And this is because you have these waves trapped in the accretionary wedge where they continuously impact and reactivate slip on the fault. And this is very important for tsunami genesis, because if you have more slip in the shallow part of the fault, you will get more uplift, and hence you get a higher wave in the ocean, and in the end, more inundation at the coast. So, does this all make sense? Is this all purely due to the waves? Yes, we can have a look at that. If we have a model where, in the dynamic rupture model, where we have no material contrast, so we're going to get rid of the accretionary wedge, everything. The slip distribution looks like this. So it's much lower, and the slip is localized in the nucleation region. If we then add a free surface, and we see that the waves can be reflected back towards the megathrust and reactivate fault slip, we see already that slip is increased, and also a bit more slip is happening on the shallower part of the fault. And then if we include our sediments in the accretionary wedge, we see slip is very much increased, and it really properly shifted towards the shallow part now. So clearly, what our geodynamic model said was very interesting, but only by specifically modeling the waves, you can get an idea of what the actual slip distribution will be. Otherwise, you might underestimate the shallow slip. So that is quite important to include those complex geometry changes. Another thing to compare our geodynamic model and dynamic rupture model is the stress drop. How similar are they? And what we see is that actually they are quite similar if we consider the dynamic rupture model before we get the most influences of the waves trapped in the accretionary wedge. So we're considering 60 seconds after the start of the rupture here. And that's in light blue, geodynamic model in dark blue. And you can see it matches quite well, with there being also a different stress drop in the sediments here in orange in the background, and a higher stress drop in the basalt in the nucleation region. Highest stress drop always in the nucleation region in this case. So similar and material dependent. So brief recap, we have now shown that we can model earthquakes over a large range of timescales, and we get spontaneous rupture nucleation and arrest in the dynamic rupture model, which is something the dynamic rupture community might find useful. And these trapped waves that we've observed in the accretionary wedge increase the amount of shallow slip and are hence important to take into account for tsunamigenesis. But I have been talking about tsunamis now, and I've promised to talk about tsunamis, so maybe we should actually get on to the tsunamis. And we do that by adding a tsunami propagation and inundation model to our modeling framework that we had. So we had our geodynamic model, output goes into the dynamic rupture model, and then the surface displacements that we get from the dynamic rupture model we use as input for our tsunami model. And we're applying this framework to splay faults. And if you don't know what splay faults are here, there is a very schematic figure of a subduction zone. We have the megathrust, which is like the interface between the subducting and overriding plate. And splay faults are these faults that splay away from the megathrust in the accretionary wedge. And as you can see, they are steeper than the megathrust. Okay, so that means that if you have an earthquake and it chooses to go on the splay fault instead of on the megathrust, and you have the same amount of slip, because this fault is steeper, you would expect larger seafloor uplift, and hence it would have a larger effect on tsunamigenesis. So that is why now that we have our three models coupled, we are going to apply it to splay faults because they're probably important for tsunamigenesis. So the way we're going to do this is we are going to take our splayful geometries from the large-scale yielding in the accretionary wedge. As I've shown you before, we don't have discrete faults in the geodynamical model, where we do see strain localization. And in the beginning, we just focused on the highest strain, and then we get the megathrust. But there's a lot of strain happening, and there's, on these large timescales, a lot of strain accumulating over time. So we can actually pick our splay faults from there. And then we get these splay faults. We pick 6 because they are kind of representative, and we take the highest strain or slip in this case. So 1, 2, 3, 4, 5, and 6. We have some smaller ones and some bigger, steeper ones. We can have a look at how they fit into the stress field in the accretionary wedge, because the idea is that so here I plot the principal stress angle, which is colored, but you can also just look at the little bar inside the circle, which shows you the stress orientation. And the idea is that here in the deeper part, the megathrust and the stress field are aligned. So this is where you get nucleation. But once you get more shallower and the megathrust becomes more and more horizontal, the stress field does not change that rapidly and still has a significant angle. And then the splay faults are the faults that align with the stress field. So the idea is, if that is the case, would the earthquake then choose to go on the splay fault because that follows the stress field and it's easier for the earthquake? So that is what we're going to investigate. So with that in mind, from our geodynamic model, we once again set up our dynamic rupture model, and we then get the following dynamic rupture model. It's more or less the same as what I've shown you before, but now we have these 6 splay faults included. And then we run it, and we can have a look at the surface displacements. So first, the model without splay faults as some kind of reference. These are the surface displacements. So this is distance from the trench, and these are the final vertical displacements. And you can see that it's more or less uniform at about 5 meters. If we have the model with splay faults, we see this. And in this model with splay faults, actually all 6 splay faults rupture in addition to the megathrust, and they rupture due to various reasons. Sometimes it's because of a dynamic stress transfer, or the main rupture immediately chooses them, and sometimes it's because the reflecting waves touch upon them from the top of the splay fault and then they rupture downwards. So there's many different ways, there's quite some complications in there, but in the end, to some extent, they do all rupture. And this is reflected in the surface displacements. We clearly see these peaks. And if we plot where we have our splay folds, our tips of the splay folds, we see that matches very well. So clearly, rupture on splay folds indeed increases vertical surface displacements. We can then check how that affects the tsunami. And I'm not going to claim that I did any of the tsunami modeling. That was all Leo. And as input, we have used these surface displacements from the dynamic rupture model. We use the time-dependent surface displacements. And this is our initial setup. We have this bathymetry that we get from the geodynamic model. And we have an initial ocean at rest. And then we can have a look at what happens with the tsunami propagation, again as a reference, the model without splay folds. Here we see distance from the trench and what happens with time. Here we have the beach, and I'm plotting the sea surface height. And we see that in the beginning, we get this large, broad wave, and that travels towards the beach. And then we have one main episode of flooding, and that is that. If we have the model including splay folds, we immediately see the effect of these high peaks. And at the coast, that actually translates into a first big flooding episode, which has much more inundation than the model without splay folds. So we see that. And then the other peaks of the smaller splay folds kind of all interfere with each other and result together in a second flooding episode. Okay, so quick recap here. We can now model tsunamigenic earthquakes and the actual resulting tsunami over a large range of timescales by combining these three models. And by applying it to splay folds, we see that rupture on multiple splay folds leads to larger surface displacements and wave heights. Now, this was kind of my main part of my PhD. But as I said, a lot of the collaborators have done really cool stuff. So I just want to highlight that. So first of all, as I said in the beginning, our dynamic rupture model is fully elastic. But Stephanie looked into what if it's not only elastic? What if we take into account off-fault plasticity? Well, I can tell you what happens. So here we have the fully elastic dynamic rupture model that looks like this, very similar to what we have seen before. And then if we do take into account this off-fault plasticity in the accretionary wedge mainly, we see this. And the first thing that we can notice is, whereas here we have an earthquake that ruptures all the way to the end of the megathrust, here it actually is stopped, which is similar to what we saw in the geodynamic model, but the dynamic rupture model, the elastic one, always had so much energy that it just broke through the velocity strengthening anyway. Not anymore when we include off-fault plasticity. Why is that? Well, a lot of the strain goes into what happens in the accretionary wedge. This is what we see in the wedge in the dynamic rupture model. So obviously there's a lot of localization of strain here, and that matches perfectly well with what we saw in the geodynamic model, where we see that we have these splay folds. And so that is another indication that the coupling worked very well, but also that if we take this off-fault plasticity into account, we actually do recreate these splay fold geometries, and we see that it also increases the surface displacements in the dynamic rupture model. So even without, in this case, specifically modeling the splay folds as a discrete fault, we can get that effect to a certain extent and increase the surface displacements locally. Then this has all been 2D, very interesting, but 3D is where it gets really cool, right? So Betsy has been working together with a lot of people to get this towards 3D. And that basically means that here you can see this 2D slice of geodynamics, which was mainly my contribution. And then that gets interpolated across the folds in a three-dimensional dynamic rupture model. And then those surface displacements get used into a two-dimensional tsunami model. The previous tsunami model that we used was 1D. Yes. So we do that, we apply it, we test a few things, and the resulting tsunamis and earthquakes are quite realistic in terms of stress drop and rupture velocity. So we kind of trust our findings, and we can now say that, oh, we actually have this whole coupling method of geodynamics to dynamic rupture to tsunami in 3D. Now, another collaborator, Aniko, who is currently a PhD in Munich, used that 3D framework and applied that to a more physical question. So not necessarily testing whether the framework works, but trying to get some answers and some interesting physics out of it. And she found out by running this whole suite of models where you can have nucleation at different locations along this 3D fault, that you can have localized up or down dip propagating supershear caused by the large-scale fault topography. What does that mean? Supershear is where the rupture velocity is larger than the shear velocity of the rocks. And that doesn't always happen, and especially in subduction earthquakes, as far as I understand, it is not that common, not that commonly observed. So in these models where we have, again, we have this fault geometry from the geodynamic model, which is not just a 3D polynomial or anything. It actually follows the stresses. We have some bumps in there, basically. And if the earthquake rupture comes towards such a bump, we see that there we get supershear. And again, this is interesting to learn and helps us in understanding how we could get supershear in which circumstances. And then lastly, I wanted to kind of look beyond, and this is really cool work by Thomas, which I really didn't have much to do with at all. But he made these really cool models of the 2018 Palu Sulawesi earthquake and tsunami. So just to give you some background on the event, there was an event in Sulawesi, Indonesia. Here, this is Sulawesi. Here you can have a little zoom, and there was a 7.5 magnitude earthquake, and this was a strike slip fault, so not subduction anymore. And usually strike slip faults aren't really associated with tsunamis because there is little vertical uplift involved, right? But the interesting thing was, even though it was a strike slip fault, there was a localized tsunami which really wreaked a lot of havoc in Palu, in the Palu Bay, and especially around this bay here. So then immediately the question was, how did this work? Why did this work? And of course, the first thing that springs to mind is, this strike slip event must have triggered a landslide or something, and that caused the tsunami in the bay, very localized, causing all this trouble. But of course, if you want to test it, you need to figure out, well, could have just a strike slip earthquake have also caused a tsunami? So that is what Thomas did. And this is the dynamic rupture model setup. So he based all his data, like the geometry of the fault and the stresses on the fault, on lots of data and literature that was available. So we look from above, and here we look from the sides. And as you can see, it's a very complex fault geometry consisting of 3 segments roughly. And if we run that model, you get very cool pictures like this. And there's lots of waves going on, very complicated stuff where the rupture jumps from one segment to another, things like that. And then if we look at how well it actually matches the earthquake that was observed, we can have a look at, for example, some SAR data. So here we have the modeled ground displacements. So here we see the fault very faintly, and on one side blue, the other side red, and this is the actual data. That looks like this. Okay, so what is the difference? Slightly smaller than the actual values, so it matches rather well. And this means that the earthquake scenario with this strike slip fault that Thomas made largely matches the key observations. So it kind of works. Then if we have the tsunami model and the model setup, we take the surface displacements from Thomas' model and we then translate that into bathymetry perturbations for the 2D tsunami model. And those tsunami models were all run by Stefan. And these are just some snapshots of how the grid specifically and the sea surface height changes over the course of the model. So it looks quite fancy. This is again the Palu Bay where it's all about. And then we can also have a look at how well our model produces the observations. In this case, a small figure of inundation level. So in blue, we have the observations for various different regions around the Bay of Palu. And then we have the inundation height that we plot here. And in orange, we have our modeled inundation. And as you can see, largely, we kind of match that quite well. So what does this mean? This means that actually you don't need an additional landslide source in order to explain the tsunami that happened due to a strike-slip fault in a very local area. Actually, it could just happen due to the complex interplay between the fault dynamics and then the bathymetry and everything like that. So that was one of the main takeaways from that project. And also, it has been modeled very quickly. So the tsunami happened, the earthquake and tsunami happened, and Thomas and Stefan were on it immediately. And they did this thing called rapid response modeling, where within a few days, weeks, months, there actually was a fully working model and coupled framework for this dynamic rupture and tsunami scenario together, which then helped us to gain some insight into this. And with the increasing computer power and methods available, this becomes increasingly possible and useful. So with that, I want to end with some conclusions. So I hope that I've convinced you during this talk that we can model tsunamigenic earthquakes and the resulting tsunami over a large range of timescales with this coupled modeling framework in 2D and 3D now. This has some benefits. For example, in the dynamic rupture model, we get spontaneous rupture nucleation and the rest. And some physical insights that we gained is that waves can get trapped in the accretionary wedge, and this can increase the shallow slip. If you include splay faults into the mix, rupture can occur on them. We can have rupture on multiple splay faults during one single event. And when that happens, it leads to larger surface displacements, more localized surface displacements, so they have a smaller wavelength. And this then also leads to larger tsunami heights. If we go all the way and we apply this to real scenarios, we have this possibility of fast physics-based response modeling. And if we apply this to the 2018 Palu Sulawesi tsunami, we see that actually it could have been sourced by an earthquake alone. There was no additional landslide source needed. And with that, I want to conclude the scientific part of the talk. And I just want to highlight that I do a lot of outreach, and I sometimes wonder why, but it's what I do. And I just wanted to draw your attention to the fact that I have started a YouTube channel, which you can go to on this link. And I talk about academia and research and what it's like to be a postdoc in geophysics specifically. And I hope it's educational and funny, and some people may find it interesting. So if you want to support that, do go there. And with that, I'm ready for questions.
Thank you. I'll applaud for everyone. Thank you very much. I'll be sure to link your YouTube to your speaker bio so people can check that out. I've seen one. They are funny. Good. Oh, we have a question already. Scott True, would you like to unmute and ask your question? Hi, Scott. Did you have a question?
I'm sorry. I was trying to hit the applause and hit the question raised hand instead. I'm sorry.
Okay. No, that's fine. All right. Well, if Scott doesn't have a question, I can start. I was curious how your plate velocity might, if there any correlation between that and like the size of the tsunami or how it's being generated. So yeah, in your initial sort of geodynamic setup, right, you're obviously giving it a particular plate velocity. And so have you tested different ones and how much of a difference is that making?
Yeah, eternal regret. I haven't tested different plate velocities yet. I do know one of my other collaborators, Sylvia Brizzi, has been doing that for a few models, I think. But I don't think she has gotten to analyze the seismic stage of the model yet. So
yes, I'm still working on that. Sorry to interrupt.
excellent.
Hi, Iris, great talk. Thank you.
Thanks, Sylvia. Well, yeah, so that, and yeah, I do think that it would change some things. Specifically, for example, the recurrence time would be a very easy thing to quickly change. I also have to say that in the subduction setup specifically, we do mostly see only scenarios where the entire megathrust is rupturing. So we see very few partial ruptures. So I'm not sure how that would change. But yeah, that's just a thing to keep in mind, that we don't fully reproduce Gutenberg Richter statistics or anything like that.
Okay, thank you. Jessica Warren, I see you have your hand raised.
Hi, thanks, Iris. That was a really interesting talk and really beautiful graphics as well. Can you comment a bit more on 2D versus 3D and the need, kind of differences between those models and the need, you know, when do a 3D needed, and you know, because I'm guessing computationally that's you know what not a universal transition that can be made.
Yeah, that's a good point. So let's see if I can go back to some of those figures. Yeah, so obviously 2D is better computationally, so it's easier to do some parameter studies, but 3D obviously is in many ways very important for dynamic rupture. Specifically, if you want to talk about the tsunami, the bathymetry and the coastline and all these very small details have been shown to be very important if you want to understand local events. For example, in the Palu Bay, obviously this is a very, very small scale detailed thing, and you would only get this really in 3D modeling. So that is specifically on the tsunami side, where I think 2D modeling can't really do it, or can't really add that much to it, because you need this 2D tsunami bathymetry and coastal structure. In terms of the earthquake, I think there is a lot of interesting stuff that can be done. For now, we have just focused. Okay, it's loaded. So for now, what we've done is we've just taken the 1D stress and strength profile and rock properties from the geodynamic model, and just interpolated that horizontally, because I mean you need to start somewhere. But obviously, it would be really cool to test lateral variations, which is probably much more realistic anyway. And then you can probably see some much more interesting things, because now obviously if we have an earthquake starting in the middle, it will be kind of symmetric, and if we nucleate it here, it will, you know, be have some larger slip here and then taper off towards the other side. But if you change your stress conditions laterally, I think that would be really cool. And obviously people have done that, specifically these rapid response and really realistic models for the Palu earthquake by Thomas, but also the Sumatra earthquake that I showed you in the beginning, which was also actually done by Thomas and Alice. And there you see that it really matters, specifically here, that you can see for an earthquake that lasts for as long as the Sumatra earthquake, it matters that it propagates along. And in these really big scenarios, that also has an effect on the tsunami. That it first starts here and then, yeah.
Great, thank you.
Thank you. James Condor, did you want to ask your question?
Yes, thanks, Iris. It's a great talk. In your 2D models, you show some strain localizations that are conjugate to your splays. I was just wondering about those. Would those presumably be normal faults? And what would they do to your surface deformations if you turned those on in your dynamic rupture models? Yes.
Yeah, these weird ones.
Yes.
So yeah, we've had a lot of debates on these with the people that also ran these models. I don't know if we are 100% convinced that they should be there. I mean, in a numerical sense, it kind of makes sense that they are there, but they're not really well observed. I mean, usually you would expect faults kind of like this, not maybe like this. So yeah, we have thought about activating those in the dynamic rupture model. We haven't done that yet. I'm not sure if they would be normal or thrust faults.
Thank you. James, did you have any follow-up, or is that?
No, that's fine. Thank you.
No, just checking. Carlos Mortera, would you like to unmute and ask your question? If not, I can read it from the chat here. Carlos, you can unmute if you want to follow up, but it says, what are your evidences for splay faults dynamics at the prisma tip near the trench they used for the models?
Right, so from data, I guess. So there have been studies on earthquakes that have been observed where people are like, okay, because sometimes, there is a tsunami that is bigger than what you would expect. So you start to look for other indications that the other mechanisms that could have made the tsunami as big as it has been based on the size of the earthquake that maybe wasn't that big to begin with. So you can either have this additional landslide source, which obviously a whole community is working on. You can also have these splay faults, and I think they have been observed. Well, they have been suggested for the Sumatra earthquake, actually. This is why in this model you actually see some splay faults here, also back thrusts, actually. So yes, they have been observed or thought to be observed there. I think they've also been inferred to be active during a few earthquakes in the Aleutians, if I'm not mistaken. Mainly though, I think where the biggest question comes from is if you do these seismic profiles, you see this very detailed look of the accretionary wedge where you have all these faults lined up together. And then the question is, are these active or not? So without wanting to say whether or not they are active at the moment for a specific setup, what we wanted to test was, could they be active during one event simultaneously? And it turns out they can. Whether or not that is actually the case. Difficult to say. Also difficult to observe, because if you look at the results from our models and the resulting tsunami models, what we see is that since if you have these multiple splays rupturing and you get all these small wavelength peaks of tsunami interfering with each other at the coast, it becomes very difficult to say whether or not whether there was one splay fault that ruptured or multiple, or so it's difficult to get a distinct signal out of the tsunami data to verify that. I don't know if that helped.
I think so. Carlos, feel free to write in the chat if you had a follow-up. So that I was actually just going to follow up on that. Does that mean the distribution of those splay faults would make a big difference, even if you can't pinpoint if it's one or the other, to the like here in your tsunami propagation, right? You sort of have a first big one, and then the other ones kind of all clumped together. So
yeah, exactly. Yeah. So what we see is that in this case, the biggest one has the most effect, but I also ran some models where I leave this one out, and then the rupture chooses this one as their biggest one, and then this results in the biggest first wave, and the others kind of interfere with each other. So yeah, I mean, these ones are a bit less steep, so obviously you would get a little bit less of a signal there. But I think in geological terms and what people do to interpret the seismic data from accretionary wedges, also another point of debate has been, are these still all active, and maybe these larger, bigger faults that are older are not active anymore, and maybe it's only the newest ones that are active. So yeah.
Okay, thank you. Are there other questions for Dr. Van Zelst? Well, I have one more, and it's just from the geodynamic perspective. So when you included the sediments, you were able to get your slip distribution to move shallower, like closer to the trench. So does it matter what kind of sediments you're using in there, or?
So again,
had to be there, yeah.
Yeah, so we did some tests on this, and again, it's mainly Sylvia who's done some really cool work on this. She looked at the amount of sediments, which then changed the geometry, and therefore it changes where you have the partitioning of seismicity. So is it mainly in the accretionary wedge, or mainly in the outer rise if you have a steeper slab, if there is not that many sediments? The effect of actual sediment properties, we have not looked into detail yet. I know Sylvia has done some models with different densities, I think, but again, hasn't looked at the seismic effect yet. I currently have a master's student working on this, because obviously this is a really interesting topic, and would be great to say something about that. Yeah.
Cool. Well, I will keep an eye out for this. Yeah, very neat stuff. All right. If there are no other questions, there's lots of messages in the chat. People enjoyed the talk. Then let's thank our speaker again, Dr. Iris Van Zelst. I'll applaud for everyone.
Thank you.
Get your virtual applause if you can see it.